Am I speaking loud enough for everyone?
Yes.
Okay, I think it's easier if I don't use a mic, but if I'm not, I'll be glad to try and use one. I'm going to talk a little bit today about when science gets it wrong, because science, by nature, doesn't always get things perfect. And I hope I don't forget this isn't a class and then I ramble on for the next 2 or 3 hours. So we'll try and go fast. We have to clip off a little something here, and I think the top is going to be better to clip off than the bottom, so we'll try it this way. I hope it works. Okay, can we go to the next? We can start back a couple of thousand years ago with the ancient Greeks. They, of course, thought that the entire world was made of 4 different elements: earth, air, fire, and water. And things that were real heavy contained a lot of earth. Things that were liquid contained water. Things that were shiny contained fire. And they also had an idea of how these things arranged themselves in the earth. Okay, next. They thought that earth, the natural place for earth, was at the very center of the universe. And the natural place for water was above earth, and air was above water, and the natural place for fire was above air. Now these represented everything near the earth, which of course was contaminated because that's where man lives. But most people think, oh, this is kind of an old theory, and kind of laugh and giggle, but you know, this was actually a very good scientific theory, because a good scientific theory explains what's known, and it also can make predictions. Okay? And so from this they can explain, why does a rock fall? Well, a rock, if you're holding it up, wants to get as close to the center of the universe as possible, so it's going to fall down. You know, if you're giving a baby a bath and they pass a bit of wind, why do the bubbles float up? Well, because the natural place for air is above water. Why does rain fall? Why do flames leap upward? Why do we have springs? These aren't boing boing springs. These are water springs. Obviously, the natural place for water is above earth, so it's coming up out of the earth so that it can be above the earth. Okay? Next slide. There was actually a 5th element, or 5th essence, called the quintessence or quintessence, but that was the material that made up the heavens. Man wasn't near this stuff. This was up in the heavens. Because it's in the heavens, it was perfect, and all things about it were perfect, so if it moved in circles, and it moved at constant speeds, and they could even explain, you know, how does the sun move during the day? Well, it moves in a circle around the earth, and the moon moves in a circle. The only difference is the sun moves 360 degrees in a day, the moon only moves about 345 or so. Okay, next one. To go along with this, gradually this theory developed more and more, and there became something known as the Philosopher's Stone. And it was supposed to be the material that helped turn base metals like lead into things like gold or silver. Of course, we know the difference between gold, say, and lead. They're both heavy metals, but the difference is gold has a lot more fire in it. So the Philosopher's Stone was supposed to help add fire to gold to make it pretty and shiny and stuff. But because it could add fire to gold and stuff, it could also add the fire of life to people and, you know, extend our lives and make us immortal, and, you know, people always wanted that too. So, philosopher's stone was something that alchemists during the Middle Ages spent a great deal of time looking for. Of course, they never found it. Next, please. We know that this whole theory was wrong. I mean, we still have atomic theory, and we know all things are made of atoms. But there's only 118 different kinds of atoms. So actually, our idea is very similar. The ancient Greeks had 4 elements. We have 118. But the idea is very similar, so we haven't gotten rid of it completely. Gravitational theory kind of explains why rocks fall, and it also explains why those bubbles rise up in the air. Nuclear science can tell us that atoms can transform from one kind to another, and that's what happens in radioactivity and some of these big accelerators, but we still can't turn lead into gold, and it's a pretty expensive way to change things. So it's not monetarily worth it here, but we can do some changing. We don't need a philosopher's stone, we need an accelerator to change atoms. Okay? Another of the great ideas from early science, this is from Aristotle. He actually didn't come up with it first, but he was a strong proponent, and he had collected works of lots of other people. And that was the idea of spontaneous generation, that life spontaneously generates. Okay? Living things come forth from non-living things because they contain pneuma, or vital heat. Remember the fire, because this is the same idea. The creature generated was dependent upon the proportions of this pneuma and the 5 elements. Of course, it really only the 4 elements near the surface of the earth. That quintessence was out in the heavens, so most of all the living things here on earth was the first 4 elements that we talked about. But it's kind of interesting on how they had this. If we look at the next slide, maggots were supposed to come from meat. You know, if you put a slab of meat out on the table, eventually maggots would seem to appear. Scallops and clams were supposed to spontaneously generate from sand, oysters from slime.
Yeah.
Yeah, lots of these are just, they're kind of related to what they look like to begin with. Barnacles from hollows and rocks, redworms from long-standing snow that is eventually turned red. I don't get that. Some grubs from fire. Okay? This, of course, was, although it was proposed a couple thousand years ago, it wasn't until the mid-1600s that we could prove that that was not the case. And good old Louis Pasteur was the one who demonstrated this most clearly in the 1860s. And if we look at the next slide, this kind of shows Louis' experiment. He took some broth and put it in a flask with a long curvy tube like this. It boiled the broth to sterilize it, and as long as it remained in a flask with the curvy tube, nothing grew in it. When he removed the curvy tube, microorganisms started to grow in the broth. And of course, what it set up is he sterilized the broth, and just sitting here, anything from the air that would happen to fall would get caught down here in the bottom of the tube and couldn't actually get back into the broth. Take that off, things are going to naturally be able to get into this broth from the air, that contaminates it and it grows. So the idea that things spontaneously generate, this showed that they don't happen, it only happens from contamination of one kind or another. Okay? It's very strange up here. I have two shadows, and I keep thinking the other one is, I realize the one, but not the other one here. Another interesting thing is to look at the various theories of light. In the late 1600s, there were two opposing theories of light. One by Isaac Newton. Newton had studied light very carefully long before his famous works on gravity and motion. He had studied optics, and Newton thought that light was best explained if it were some kind of particle. But a contemporary, Christian Huygens, had done similar experiments and thought that light was best explained as a wave. And so if we look at the next slide, we can see some of the properties of light that were known at the time. Light comes in different colors. Light reflects. Light refracts. That means it changes direction as it goes from one material into another. Light beams can pass through one another. Light travels in straight lines. Travels through space and travels at a very high speed. They actually knew this at the time. Galileo had actually tried to measure the speed of light. He and an assistant had some lanterns that they could operate the shutters on these lanterns very quickly, and they practiced in a room so that Galileo could open his shutter, and his assistant, as soon as he saw the light, would open his shutter, and Galileo would look, and in a room they could get it so it almost seemed instantaneous. And then they went out on several on different hilltops several miles away and tried it. And Galileo's conclusion was as follows. Light travels instantaneously or at such a high speed that it's undetectable in this experiment.
And he was right.
And he was perfectly right. That's a perfectly good conclusion to draw. Actually, by about this time that Newton and Huygens were arguing over the nature of light, light was first measured. It was first measured astronomically. A fellow by the name of Romer noticed that the moons of Jupiter eclipsed one another, and as we were close to Jupiter, they would eclipse at a certain rate, but as we moved further and further from Jupiter, it was taking longer and longer for them to eclipse. And then as we'd move close to Jupiter again, they would get faster and faster. And he realized that the difference was the light was having to travel across the orbit of the Earth. They knew the rough size of the Earth's orbit at the time. The difference in time was about 16 minutes, and so they figured it out, and he actually had a reasonably good estimation for the speed of light. But he could only do it in outer space. They couldn't do it here at the surface of the Earth, but we knew it traveled through space to do that, and we knew it traveled very quickly. So, let's look over here and see how the Huygens and Newton might have explained these various things. Neither of them had any difficulty explaining colors. Newton said colors are easy, they're different sized particles. Huygens said colors are easy, they're different sized waves. So, no one had any trouble explaining that. Particles bounce off of things. If you've ever played pool, you know you can shoot a ball and it hits the side rail and it bounces off. And it bounces off just like light bounces off a mirror. It comes in at one angle and it leaves at exactly the same angle, unless you're using English or something tricky like that. But waves also bounce off in exactly the same manner. So both waves and particles could explain reflection easily. Light changes direction. If we think about how light would change direction as it goes from air into water, we've all seen, you know, a glass with a straw in it and the straw looking bent or something like that. To explain how light changes direction as it goes from air into water, Newton said, well, particles would have to speed up. We've all seen this, particles refracting. If we've ever played miniature golf, you know, and you're up on one level and you're trying to hit the hole down on another level and you hit it and it rolls down an incline and it doesn't go in a straight line and angles off. Huygens said, well, we can explain the way light bends when it goes from air into water if we think of it going from fast to slow. So this actually gave us a way to tell the difference between particles and waves. The only problem was, at the time they could only measure the speed of light in astronomical distances, and we couldn't measure the speed of light in air, and we couldn't measure the speed of light in water. It's real hard to fill the orbit of the Earth with water or something like that. So, if we go to the next slide. The next slide caused a bit of a problem. Next problem of light beams passing through one another, because particles bounce into one another. But Newton kind of jumped up and down and waved his hands and said, we can explain that by assuming that particles are very, very tiny, and so they're very unlikely to hit one another. Light traveling in a straight line was easy for Newton to explain with particles, because particles do travel in straight lines. We're cut off down here further on the bottom, but light traveling through space, well, particles can travel through space. The Earth is a big particle. Yeah, it's kind of cut off on our thing here. But the Earth's a big particle. It travels through space and stuff. Lots of particles travel through space, and traveling at high speeds, well, if the particles have to be very small, then it would be pretty easy to get them going real fast. And so he didn't have much trouble with that. Huygens, when he explained this, okay, let's go to the next slide. He had no problem with light beams passing through one another, because waves can pass through one another. And they do all the time. If you've ever been at the shore, you can see some waves going in one direction and some waves going in another, and they just pass and keep going. So that was easy. But he had some difficulty with light traveling in a straight line, because waves, if you've ever thrown a rock into a lake, the waves don't go in a straight line, they move out in circles, they bend. Okay, we call it diffract. And since light seems to travel in a straight line, Huygens had to jump up and down and wave his hands and say, well, the reason it seems to go in a straight line is because the waves are very, very short. Okay. Short waves don't bend nearly as much as long waves. You're all familiar with this when you have the kid in high school who has just gotten his first car, you know, for 95 bucks and put in a $595 sound system, and they pull up next to you, what sounds do you hear? You don't hear any treble, all you hear is the whoa, 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 whoa. And that's because low-frequency sound waves are long and bend easily. The high-frequency sound waves just bounce around inside the car and never come out. But the problem of traveling through space also caused Huygens some problems because waves have to have something to travel on. Water waves travel on water. Waves on springs travel on springs. Sound waves travel through air, you know. What did light waves travel on?
Ether.
The luminiferous ether, exactly. And this had to be a material that permeated all of space. And to explain how light traveled at such a high speed, the speed at which a wave travels depends upon two things. Not the wave, but it depends what it's traveling on or through. The less dense, the faster a wave travels, and the more rigid something is, the faster a wave travels. So to travel at the enormous speed light has to travel, this luminiferous ether has to have an extraordinarily low density and an extraordinarily high rigidity. Not something we normally associate together. And so there were problems with both of these theories of light. And for the next 100 years, it was debated. But the debate fell into politics. If you were English, you said, well, Newton said it was a particle, it must be a particle. But Huygens was Dutch, he was from the continent, so if you were on the European continent, you always were kind of against the English. So, of course, light is a wave.
Yep.
And so it was a political discussion rather than a scientific one for about 100 years. And then, next slide please. Thomas Young came along. Now Thomas Young is one of the great scientists most people haven't heard much of. This is a biography, and I love the name, The Last Man Who Knew Everything. Okay.
Yeah, right.
Young did an experiment on light that kind of settled things. He was also a physician, and he was also the first person who could start to read Egyptian hieroglyphics. Because at about that time, in the early 1800s, the Rosetta Stone had just been discovered. And it had this black stone with 3 different languages in it. And Young was the first to realize that maybe all 3 languages were saying the same thing. One of the languages was ancient Greek, and people could still read ancient Greek, even though no one had read Egyptian hieroglyphics for a couple of thousand years. So he started reading. Nowadays, we have followed his lead in Egyptian hieroglyphics. We can read quite easily, but he was the first modern man to read Egyptian hieroglyphics for almost 2,000 years. But if we go on to the next one, Young came up with an experiment. This is typically how it's shown. He took sunlight and passed it through a tiny hole and then allowed it to fall on 2 other holes. If light was going to be a particle, we know how particles travel. They travel in straight lines. And so light, we would have light down here and light up here, and everything else was going to be dark. But if light was a wave, it was going to spread out. And right in the center were equal distance from both slits. So a crest from the top and a crest from the bottom would meet, make a super big crest, and would have light in the middle. And then if we move down just a little bit, we're a little bit closer to the bottom slit than the top slit. So by the time the crest from the first slit gets here, the crest from the bottom slit has reached there and moved on. And so a trough from the bottom slit was there, and they would cancel and they'd get black. And so basically what Young's experiment was, it was a way to test between particles and waves. By the way, Young was an Englishman, which also helped this argument. If light was going to be a particle, you should see two bright lines. If light was a wave, you would expect alternating bright and dark. He saw alternating bright and dark. And so, next slide, please. It showed that light had wave properties. And throughout the 1800s, lots of people worked with light waves, learning new things. Infrared and ultraviolet had just been discovered, but now they were easily explained using Young's experiment. He could even measure how big the wavelengths of light are. So you could use that to measure the wavelength of infrared and ultraviolet. A famous American scientist in the mid-1800s was A. Michelson. And he was famous for a number of things. One of the first things he had invented was something called an interferometer, which made use of the wave properties of light. And he could use it to measure very small things. If I go up and press on this wall over here, most of us are going to say nothing happens. But in reality, that wall does give just a very small amount, and he could actually, with his interferometer, measure how much that wall moves, even if it's solid brick, when I push on it. And I'm assuming I'm in my mild-mannered science teacher, not my blue underwear with a big red S on it. He also became very famous for making a number of more and more accurate measurements of the speed of light. But one thing that he failed at is he used his interferometer to try and measure the passage of the Earth through the luminiferous ether. And every time he tried, he failed. It was one of the big failures of his life that thought at the time. Things were later explained, however, in the next slide, by another young man in 1905. Now remember, this is about 100 years after Young had proved that light had wave properties. In 1905, Einstein produced three famous papers. The one everyone knows about is the one on special relativity, which gives us E equals mc squared. But that theory was able to explain why he got a null result on trying to find the ether. Because with special relativity, we assume what's constant is not time and space, but the speed of light. And therefore, it makes no difference who's measuring the speed of light. We'll be getting the same answer, no matter how they're moving. But the other paper was the one that he did eventually win the Nobel Prize for. It's interesting, we all know about E equals mc squared. He didn't win the Nobel Prize for that. He won the Nobel Prize for explaining the photoelectric effect. If you shine light on a piece of metal, red light won't do anything, but violet light will start to knock electrons off the metal. And it can be very bright red light and nothing ever happens, and it can be very dim violet light and electrons will start to be knocked off. People couldn't explain it, and Einstein said, well, that's because light is exhibiting particle properties. It's kind of like if I have a Nerf gun and I fire it at the wall. is that going to chip away at the wall at all? No. If I do it 1,000 times, it's still not going to chip away at the wall. But if I take one, 45 caliber handgun and fire it at the wall just once, I'm going to do some chipping away at the wall. And so Einstein said the photoelectric effect is where light is showing particle properties. So here we are. A couple hundred years ago, they had said there was a big fight over whether it was a wave or particle. Then Young came along and proved that light had wave properties, so everyone assumed that that meant it didn't have particle properties. Then Einstein comes along and proves that light has particle properties. Since then, we've been left with what we call wave-particle dualism. If you do an experiment to show that light has wave properties, you get a positive result. If you do an experiment to prove that light has particle properties, you get a positive result. Light has both wave and particle properties, and that's hard for us to get through our minds. But light doesn't care what we can easily understand. Light's going to behave the way it wants to behave. Okay, next one. And this is the one I've always had the most trouble with, phlogiston. It was proposed in the late 1660s, so about the time that this argument about light was going on, and it was supposed to explain how things burned. Phlogiston was a material that things contain, and when they burn, the material released the phlogiston into the air. Okay, so burning was the releasing of this phlogiston stuff into the air. But the air can only hold a certain amount of this phlogiston. So if you have a small container and you set fire to a piece of paper inside of it, it won't burn completely. Because when the paper burns, it releases phlogiston. And in a small container, the air can only hold so much phlogiston and it stops. In a bigger container, it burns more completely. We ourselves, as we're living, are constantly, since we're warm-blooded, we're constantly releasing phlogiston into the air, okay? And if we get shut up in a very small room, after a while, we can smother because we can no longer get rid of our phlogiston and get it into the air. When metals such as iron rusted or magnesium burns were both cases where the metal was releasing phlogiston into the air. The problem is that if it's releasing phlogiston, it gets heavier. Rust is heavier than iron. Magnesium oxide's heavier than magnesium. So there was some problems with weight. We're getting rid of something and things are gaining weight. Did that mean phlogiston had anti-weight or something? Well, we can all see there's some problems here. But that was solved relatively quickly, about 100 years later. Next slide, please. By Lavoisier. Lavoisier was one of the first modern chemists, and he would very carefully measure masses of things. So he would do experiments with burning, and he was able to show that when things burn, the total weight remained the same. We may have different materials, but the total weight remains the same. The idea of conservation of mass comes from Lavoisier's experiences and stuff. He was one of the greatest scientists of his time. but he lost his head during the French Revolution. And by that I didn't mean he got very excited. I mean he lost his head. Okay, he was from the upper class, and he was involved with tax collecting before the Revolution, and you know, people don't like tax collectors, so he literally lost his head during the French Revolution. His wife was, I think, 13 when they first got married, but she was very interested in all of his work and actually took lots of records and stuff when he was in the laboratory. So she was actually a collaborator with him on it. She didn't lose her head. Getting closer to science fiction. Martian canals. 1877, an Italian named Schiaparelli first looked at the moon through a high-powered telescope and said he thought he saw some canali, which translate to canals in English, so that means there's got to be water somewhere. And next slide. Percival Lowell was one of the major Americans that was very interested in these Martian canals because he thought that they were carrying water from the northern and southern parts of Mars to the more arid parts towards the center, and they had been built by an intelligent civilization. And so in 1894, Lowell built himself, he was rich, and he built himself an observatory. And this was the first modern observatory. It was built in Flagstaff, so it was almost 7,000 feet in elevation. And at the time, Arizona had very clear skies, and it was ideal observing. You know, most people made telescopes and observatories in big cities because it was convenient to get to them. Lowell built the first modern observatory, and then for the next 15 years he studied Mars and tried to make intricate drawings. Of course, Lowell was wrong, but the Lowell Observatory still exists, and in 1930 it's where Clyde Tombaugh discovered Pluto. Of course, Tombaugh was a janitor at the Lowell Observatory at the time. A couple of years later, he went back to school to actually get a degree, but Tombaugh did discover Pluto at the Lowell Observatory. So while it was built to map Mars and its canals, it did give us a planet, and I'm sorry, all of us grew up with Pluto as a planet, so I didn't call it a planet.
It's a planet.
Of course, we have much better astronomical observations now from satellites and probes that have actually been on there. There are no canals. They were an optical illusion. Lots of people tried to map the canals of Mars, but none of the maps map. Okay? Each person thought they saw different canals and stuff, optical illusions. But we do know, here's a modern close-up photograph of Mars. We do know that there's lots of canyons and stuff like that that look like running water. And of course, just a few weeks ago, they found evidence of running water near the surface of Mars. Although it's not enough to make these kinds of features, it does imply that Mars, at least at one time, had running water at its surface. Okay? Next one. There's lots of other controversies. In the 1800s, phonology was real popular. Remember, that's where they could tell what kind of person you were by feeling the bumps and stuff on your head and stuff. We don't have to go back to the 1800s. Most of us in this room can remember the announcement of cold fusion about 20 or 25 years ago. Phrenology has not had much support and of course has died away. There is some research still going on into cold fusion. It's doubtful that the original announcement was true, but they thought there was something there. A few people have been continuing some research. Vaccines cause autism. There was a scientific study that showed that vaccines or linked autism to vaccines. Since that time, there's been many other studies, and they have never found any link whatsoever. And the guy who originally published that article was shown to be fraudulent, not just there, but in others, and has lost his medical license. And so I would tend to probably go that vaccines do not cause autism, but they do save lots of lives. I've got my flu shot right here. I just saw this on
Yes.
Yeah, obviously.
just a couple of days ago that bras cause breast cancer.
What's his
I'm
name?
kind of wondering about those men who get breast cancer. I wonder how that happens. I don't know. Global warming right now is a big controversy.
Not scientific concept.
Some scientists feel,
Yes, it is.
or a majority of Earth scientists feel that it's positive. Some scientists feel there's nothing there. Right now, the argument is kind of like the argument with light. It was mostly political. However, we'll find something here, I think, in the near future that will decide completely in one way or another. Continental drift or plate tectonics was also something that caused lots of controversy. It was first proposed about 100 years ago by Alfred Wegener. Wegener was a German meteorologist, but he studied lots of things, and he first came up with the idea of, he called it continental drift, the continents moving around on the surface. All the geologists of the time ignored him. First of all, he wasn't a geologist, he was a meteorologist. What does a meteorologist know about rocks? But Wegener had no way of explaining how or why these move. In the 1960s, they started to understand convection currents in the mantle of the Earth, and they found that they could be moving the continental plates. And so since about 1970, this has been one of the dominant theories of Earth science. But this is a case not where they got it wrong, but where science actually got it right, but people didn't believe them at the very beginning. One more. Okay. The hollow earth has actually been a legitimate scientific theory for the last, proposed by some very famous scientists during the last 300 or so years, that the earth is actually hollow. There are openings to the interior of the earth at the North and South Pole. And I once found a book in Colorado Springs at the old Chinook bookstore. And I was just amazed, and I never bought the book. And Connie finally found me an original copy of the book, the first edition. But it goes and explains, you know, mammoths that are frozen up in the tundra are not really animals from a long time ago. They're actually elephants from the interior of the earth that have wandered out through the openings. And of course, it's cold near the North Pole, and so they've gotten frozen when they got out of the interior of the Earth. He has some other ideas, but the most important in this book that I read, The Hollow Earth, he was trying to explain where flying saucers come from. They come from the civilization in the center of the Earth, and they come out through the hole to check on us because they live in the same Earth we do and stuff.
Oh, really?
We constantly hear about this. Red wine and health, you know, it's supposed to be good for you, but it does contain alcohol, and alcohol isn't supposed to be particularly good for you. So the health benefits of red wine are still kind of questionable. Franklin thought that electricity was a fluid, and everything contained some of this fluid. Some things contained just enough of the fluid, and they were neutral. Some contained too much, and so he called that plus electricity because it had an excess. Some materials contained too little of this electrical fluid. He called that minus because it didn't have quite enough. We now know that that electricity is not a fluid at all, but it's interesting because we still use his terms, plus and minus, to describe electricity. So even though Franklin was wrong, we're still using his terminology, and I think for a long time. People think that the plus and minus means something special. Actually, they're just names. They could have been called Brunhilde and Hildegard or something like that, but plus and minus are much easier to say. And you know, what killed the dinosaurs?
Smoking.
Yeah, they were probably smoking out behind the gym or something like that. We think we have an idea that some kind of astronomical object collided with the Earth. Some people have called comets or meteors, asteroids, something like that. What we really know is that there was a sudden climate change at the time, and the dinosaurs weren't the only things that died. There was a mass extinction of a variety of species at the time, and these catastrophic, almost instantaneous explanations are perhaps the easiest, but if you look, you'll find a variety of people claiming they found where the asteroid, the comet hit and stuff like that. So we're still not completely sure exactly what killed off the dinosaurs, but I would like to point out that I had to go online and I got this picture of the Stegosaurus for one particular reason. By the way, the Stegosaurus was not killed off. It had died off before this mass extinction. And the mass extinction that coincided with the dinosaurs is not the greatest mass extinction the Earth has had. There's been 3 or 4 other ones, and 1 or 2 of them have been much bigger than the mass extinction with the dinosaurs. But I got the picture of the Stegosaurus for one reason. The Stegosaurus is the Colorado State dinosaur. George? Okay. I think I'm getting pretty close to the time. I could answer a few questions, or him and haw about an answer to a few questions. If anyone wants to. Yeah.
As I understand, the ancient Greeks had worked out that the fixed stars had to be so far away that compared to the size of the Earth might as well be a mathematical point. In other words, they figured out the stars were incredibly far away. Who was the first to make the connection then well, gosh, then they must be nearly as bright as the sun. Who was the first to
I don't
float that
know.
idea?
One of the reasons they knew that they were pretty far away is because they seem to move across the sky, but we could think of it in terms of triangulation. At one time, say in the early evening, we're at one side of the Earth looking at the star. In the morning, we're on the other side of the Earth, and the Earth is big. They thought the Earth was big. In fact, the first measurement of the Earth was actually a pretty good measurement. And the Greeks knew from Gibraltar all the way around kind of China, they called it India, but China today, and they knew that was 13,000 miles, and they thought, the Earth 25,000 miles around? It's twice as big as what we know about. We're much smarter than that. So they redid the measurements and only got about 17,000 miles around. And that's the value that Columbus was using when he sailed across. And so after sailing about 3,000 miles and hitting land, he thought, well, this is about right. So it's interesting, ancient people knew the world was round. The idea of the flat Earth has not been a scientific one in many thousands of years.
Of course, you saying that if there's a measurement of 25,000, they can't drive.
Right.
That's one of the hazards of science.
That's right. That's starting off with the prejudice.
Yes.
And, you know, if you want to find the Earth is a little bit smaller, I'll measure it and I'll get it smaller for you. Unfortunately, it's still 25,000 miles around, no matter what you measure.
What is the most useful mistake that you can think of right now?
Oh, dear.
Microwave oven.
Well, I do think the controversy with light has really given us a really good understanding of things, because we are so convinced that we know everything. And the idea that light, not only light, but even things we think of particles, also have wave properties, that everything has both particle and wave properties at the same time. I think that's one of the biggest advances in science we've had. And just kind of show you, we know a microscope uses light to look at small things. But if we have something really small, we don't use light, we use an electron microscope, and electrons are particles. But we're using the wave properties of electrons.
Just of the examples you gave, the electricity as fluid is still a useful concept.
Oh, you know, it's not a bad way of looking at things when electricity moves, because even though it's going in small particles, they're so small, it's kind of like sand. Can you pour sand? Sure, sand pours pretty much like water does, because it's made of a bunch of small particles.
Epicycles are useful.
Huh?
Epicycles are useful.
Yeah. Someone else had a question.
Yeah, just a comment that Einstein's refusal to accept quantum mechanics probably was the most creating the most fruitful consequences in the last century.
Well, it's certainly one of the ones that physics has been fighting with for the last 100 years or so. At the very beginning, I started passing around the squares. Oh, someone brought him up here? Thank you very much. I'll get out of here so the next can go.
Thank you.